Okay, so today we're going to start talking about tangent lines of curves. What is meant by a tangent line is the line sharing a common point with a curve or surface and being the closest linear approximation to the curve or surface at that point. So you saw in geometry when you did segments and circles, you saw like tangent, tangent, and secant tangent. And we talked about how a tangent hits the curve at a single point. That was our definition at that time. Well, we're getting a little bit more complex definition now of what a tangent line is. In the circle, you see that on the left, we've got that tangent line hitting at one point. Because functions, though, could go up and down, it might not necessarily just hit at one point, but where you're trying to approximate the function at that location, it should only hit at one point. So, for example, at P there, each of those, the blue and the red, hits the graph just at one point near that part of the graph. Which one, though, would be our tangent line? Well, if we think to the fact that it needs to be a linear approximation of the graph at that point. So basically, if we zoomed in really close, one of our lines should look very similar to the graph. With that being said, that means the red one is the tangent line. So in other words, the tangent line represents the slope of the graph at that point. If we zoom in close enough, the tangent line and the graph should look very similar at that point P. So if we had a curve such as this, and we tried to draw in the tangent line at each of those points, we would need to draw in a line that represents the graph at that point. Or think of it as the slope of that tangent line should be the same as the slope at that point. So our leftmost point, we would have a horizontal tangent line, because where it turns from increasing to decreasing at that instant, it's horizontal. At our second point there, we would have something like the green line. Okay, at that instant, it roughly represents the slope or the graph itself if you zoom in far enough. And at the third point, we would have something roughly like the red line here. So that tangent line should be a good approximation of the graph at that instant. So when we say at that instant, we mean the slope at that instant and what the graph, if you zoomed in close enough, would roughly look like. Okay, and there's another picture of it there. So what we are going to be tasked with now is we're going to write an equation of a tangent line for y equals x squared at the point 1, 1. The issue is, for a line, we need a slope and a point. Well, we have a point. We have 1, 1. The problem is, we, at this time, don't know how to find a slope at a single point. We only know how to do it if there's 2 points. What we can do is we can use the secant line to help us out. A secant line is one that hits the graph twice. What we can do is we can make that second point pretty close to the point 1, 1. So we're going to have Q represent that point. So we're going to say it's some x value close to 1. The y value must be whatever x is squared, because our equation is y equals x squared. So for example, if we put like 2, it would be 2 comma 4. If we did 1.5, it would be 1.5 comma 2.25, because that's what 1.5 squared is, and so forth. So in general, it's x comma x squared. So what we're going to do is we're going to, in general, find the slope between points P and Q. So we'll just do change in y over change in x. So we are going to have x squared minus 1, that's our y's. And then we'll have x minus 1. So this is an equation for our slope. It represents our slope no matter what x value we pick in our picture right here. And again, our goal is to get x closer and closer and closer to 1. So what we're going to do is we are going to put this in a graphs page, and we are going to look at the table to see what this does approach when it gets closer and closer and closer to 1. So we'll go to our calculators and add a graphs page. And we'll put in x squared minus 1 over x minus 1. And then we're going to look at the table. So we'll do a Control T. Now, the table by default only shows us whole numbers. We want to be able to get x values that get really, really, really close to 1. So we're going to change our table settings. We're going to go Menu and go to Table, and we can edit our table settings. If we want to be able to tell the table what x value, we want to switch our independent to ask. That allows us to put in whatever we want for x. You want to leave the dependent on auto, though. So we'll now say, well, let's pick an x value that's pretty close to 1. So let's start with 2. So we get back 3. So let's do x. And we're going to call our y value m, because our function value is actually our slope. So when we put in 2, we got back 3. Saying if we use the x value of 2, so the point 2 comma 4, our slope between that and 1, 1 would be 3. Well, we want to get closer. So let's now put in like 1.5. Well, now we get 2.25 back. So when we put an x of 1.5, we get back a 2.25. What we'll do is we'll keep getting closer and closer to 1. So maybe we'll put in 1.1 and 1.01 and 1.001. So our x values are getting really, 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 really close to 1. So we'll have 2.1, 2.01, and 2.001. And that was for our 1.1, 1.01, and 1.001. Well, we also want to look at coming from the other direction. We were coming towards 1 from above it. Let's look at below it. So we'll look at 0. Then we'll do something like 0.5. Then getting closer, we'll do like 0.9, 0.99, and 0.999. And again, our y values in our table will really be our slope values. So if we go to our table again, we can put in 0, gives us back 1. We said we're going to do 0.5, 0.9, 0.99. And we'll write those down before they get split up. So we had 1, 1.5, 1.9, 1.99. And then we'll do the 0.999, and you kind of see the pattern. So we get 1.999. So what we can do is we can look and see, as our values get really close to 1 for the x, what does it appear our slope is getting close to? And if you look, it looks like from either side we're getting closer and closer to 2. So how we would write this, we would say our limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2. Now this is a notation we're going to use a lot in our upcoming unit. Limit as x approaches 1 means as your x values get really close to 1 from either side. So that's why we looked from both sides. We want to see what does our function value approach. Well, we set our function up to be the slope. That we purposely did that. And we found in our table that it ended up being 2. So we know that our slope of our tangent line must equal 2 when we get closer and closer to it. And we know that the point we were looking for is 1, 1. So we are now just going to write the equation of a line. Usually we're going to do this in what's called point-slope form. So just to review that for a second. Y minus y1 equals m times x minus x1. If we had, say, a slope that was 3 and a point that was negative 1, 2, well, your equation would be y equals, we'll do minus the y value. This will be our y1, this will be our x1. Oops, sorry, not y equals, y minus the 2, because this was our y1, equals our slope of 3 times x minus our x value. Well, minus the negative 1 will really become a plus 1. And you can leave your equation of the line just like that. This is point-slope form. If you want to, you could distribute the 3 and add over the 2 to get it in slope-intercept form, or y equals mx plus b, but you do not have to do that. So just one more example. If we knew a slope was, say, 1/4, and we were looking at the point negative 3, 6, we would have y minus 6, because it's y minus our y1, equals our slope of 1/4 times x plus 3, because it's minus a minus. And that would be our equation. So now going back to our example, we had a slope of 2 and a point of 1, 1. So we will have y minus 1, because of this one, equals 2 times x, and using this one now, we'll have minus 1. So what this is the equation of the line that would best represent our graph at that instant of x equals 1. The slope represents the slope at that instant, and if you zoom in close enough, this line equation would look just like our graph. Now, you might not always have an equation. You might just have, say, a table. Let's say we wanted to find the slope of our tangent line, and we're just going to do the slope here. We're not going to find the whole equation. But let's say we want to find the slope of our tangent line at 0.04. Well, we've got a graph, we've got a table, but we don't know what the equation is. What we can do is we can find the slope of the secant line with the 2 points above, and then also do the slope of the secant line with the 2 points below, and then average that, and that should be a pretty good approximation of what our slope is at that instant of 0.4. So using our green ones there, the 0.02 and the 0.04, we can say that our slope is 81.87 minus 67.03 over 0.02 minus 0.04. We can plug that in, and we would find that our slope for those two is negative 742. And that makes sense. Our slope looks like it should be negative there. It's a decreasing function. Our slope for the other one, we could do 67.03 minus 54.88 over 0.04 minus 0.06. If we plug that in, we get minus 607.5. So really what we found is two different secant lines. We found the secant line from here to here, and then we also did it from here to here. And we're going to take the average of those two slopes, because one should be a little too steep, one should be a little too flat. So if we average them out, it should be a pretty good representation of our slope exactly at 0.04. So we'll just do negative 742 plus a negative 607.5 all over 2. And that will give us that our slope is negative 674.75. So in other words, about a slope of negative 675. Now, the downfall with this is our slope, it's not quite as exact as the other one because we're kind of making approximations from our table and taking the average to kind of guess what it would be, but it should be pretty close. If we have the equation like we had in the last example, we could be much more exact as to what our slope is. Now, our slope or our rate of change can be thought of as a velocity. The difference between average velocity and instantaneous velocity. If you're finding an average velocity, you're finding the secant line. The reason being, it's the velocity between 2 points. So you're doing like distance 1 minus distance 2 over time 1 minus time 2. So these are like a change in y, like over a change in x. So in other words, this is a slope. And we'll just say of distance function. So what this really gives us is it gives us the slope of the secant line. So this process here would be the slope of the secant line. And that's what we did in the x squared example. We did the slope of the secant line, and then we just made the second point get closer and closer and closer to 1. Now the instantaneous velocity, that's at any given instant. So if you look at your speedometer, that's what it says at that time. So this would be whatever the speedometer needle would say. So on your car at any instant, if you look at the speedometer needle, that's your instantaneous velocity. What we have mathematically, that's the slope of the tangent line. And this is what we're going to be working with mostly, is the slope of the tangent line. And we just showed 2 different ways we could find that. If you have an equation, you could do slopes of secant lines, but get the second point closer and closer and closer to the point that you want to work with. Or if you have a table, you could take the point you want and the point before it, find the slope. The point you want, the point after it, find the slope. And then take the average of those slopes, and that should approximately be your instantaneous velocity, which is the slope of your tangent line. Now, our first case is the better scenario if we can actually have an equation and pick things closer and closer and closer to it. So one example with a velocity, let's say we want to find the instantaneous velocity at, say, 5. So to approximate that, and this is kind of what you did if you're in Regents pre-calc last year, we can take 5 and then take a point really close to it, like 5.01. You can plug 5 in and see what you get back for the y value. So when we put 4.9 times 5 squared, we'll end up getting back 122.5. Okay, and again, that's just from plugging in for t in our equation. We can find the other y value by just putting 5.01 in, and we get 122.99049 or so. And then we can just do the slope from there. So do your 122.99049 minus 122.5. And we'll put it all over 5.01 minus 5. When you do that, we should get approximately 49.049. What this is representing, we're doing this, we pick something really, really close to represent our instantaneous velocity. So that should be the slope of the tangent line if we looked at the graph. So it looks like it's pretty close to 49. So we did one by hand. Let's look if we just put it in a table like we did with the x squared example. If we picked 5 and 6, we would have gotten 53.9. If we had picked 5 and 5.1, we would have gotten 49.49. 5.05, here's the one we calculated, the 5.01. If we go to 5.0001, we get 49.0049. So we can say this now in terms of a limit. Our limit as t approaches 5 is just 49. Okay, these t values here we plugged in as 6 and 5.1, 5.05, 5.01, 5.001. The limit again means what is it getting closer and closer and closer to. So therefore we can say that our velocity, our instantaneous velocity, is the limit of the average velocity. Our average velocity seems to be approaching 49, so therefore we can conclude that our instantaneous velocity would be 49. And here's just a picture to represent it. The picture on the left, that's our secant line when we have 2 points. As we bring that value q closer and closer to p, the blue line slope should be closer and closer to what our red line on the right-hand side slope is. So we won't ever get it exactly, but that's why you look at it and see what it's approaching. Because whatever it's getting closer and closer and closer to, you will then be able to make a conclusion of what the instantaneous velocity, or in other words, the slope of the tangent line, actually will be. So in general, what we did today is if we keep picking a point for q that's closer and closer to the point we want, which is p, we can see what those slopes are getting closer and closer to in our table, and that will allow us to determine what our slope of our tangent line will be. And that's all for today's video. We'll see you next class period.